So we know that magnetic fields surround magnets, but there's another way to induce magnetic fields, and those magnetic fields appear when we have moving charge. Moving charge also creates a magnetic field similar to a metal magnet that would produce its own natural magnetic field. This is an induced one. We are going to represent magnetic fields with the variable B, and the unit for magnetic fields is the Tesla, which is represented by capital T. There's a series of rules that we're going to talk about that help us understand and remember when and where and how induced magnetic fields work based on moving charge. That moving charge could be a particle, and that particle could be like an electron or a proton, or it could be more broadly like a current, which we would call just like I from a circuit or a wire or something else. Doesn't really matter how we break it down, it's all a result of moving charge, and that moving charge creates a magnetic field. So our first right-hand rule is that when we have a moving charge like a current, we are going to first state that this is in terms of positive charges moving. This is known as conventional current. If you were talking about moving electrons, all these rules would flip. The right-hand rule is for conventional current. So if we have charge moving, this picture is through a wire, our fingers represent the direction of the magnetic field in this circular shape curling around our wire. We can measure the strength of that magnetic field with our equation B is equal to mu naught times I over 2 pi r. So B is our magnetic field. I here is our current. Why 2 pi r? It's a circular shape. So r is our distance from the wire in this case. And we have stronger magnetic fields closer to the wire and weaker magnetic fields further from the wire. So like in that location versus that location, we'd have a stronger field and like a weaker field out further because it's further from the moving charge. And lastly, that mu naught that's in here is the permeability of free space, which is basically how well the magnetic field can exist in air or in our free space that's available. And this is kind of a strange constant because it's 4 pi times 10 to the negative 7th. And the unit on it, if we look at our equation, is the Tesla times meters over amps. So that constant has amps in the bottom because current is on the top of our equation, and then meters on the top because the R is in the bottom of our equation, and then the Tesla is in there to make sure that works out because that's what we're measuring our B field in. And when I say B field, I just mean the magnetic field. Our second right-hand rule is for this thing called a solenoid. And that is just sometimes there's nothing in the middle at all. It's wrapped coils of wire around and around and around and around, making this sort of spiral shape like we see in the picture. So in that picture, this is a great example of how we make like electromagnets. Electromagnets are something that are not naturally conductive metals that we create a magnetic field to utilize by giving it a current. So in these solenoids, we have our second right-hand rule. This time our fingers wrap in the direction of the current around the loops, And whatever way our thumb points in coordination with the fingers curling with the current, our thumb points toward the north end of the magnet that is created by the solenoid, just like we see in the picture. Mathematically, we can calculate the strength of that magnetic field from the solenoid by again using our permeability of free space multiplied by N and then multiplied by the current. So what is N? N is like the density of our loops. So what is N really? N is also sometimes seen as capital N over L, and that is the number of loops and the length that those loops exist in. So this one, the loops are pretty spread out. It's very common to see them really tightly wound, and sometimes to increase the length, they're actually like double wrapped so that there's two layers of loops to create a stronger magnetic field. These solenoids are great to create electromagnets when we run electricity to get that moving charge to create our magnetic field. We're just concentrating it in a way that is useful compared to the right-hand rule where it's just sort of one wire or one charge. This is many, many, many of them that we're sort of stacking on top of each other in layers. And so our last right-hand rule is for the force on a particle or wire that's carrying current. And the important distinction to make here is this magnetic field is not its own. This is traveling through an external field. It will feel a force. So the two right-hand rules, sometimes you'll see this one on the bottom with the two fingers and the thumb. One is for the force felt, one is for the direction of the field, one is for the direction of the current. That one's a little tougher until you've taken some upper level math courses where you learn more about the X, Y, and Z axes. I prefer the picture on the top. Our thumb points in the direction of the current, and then the like field lines, we have our fingers point in the direction of our field from north to south, and then the palm pushes in the direction of the force. So again, this current is for positive conventional current. If you wanted to think about electron flow, you would just use your left hand and follow the same rules. So mathematically, the force from that magnetic field on our wire would be the strength of the magnetic field multiplied by the current running through the wire, multiplied by the length of wire that's in this external field. And if we do some arranging and substituting, the particle version of that is that if we have a force from the magnetic field on our particle, it's the charge of the particle and it's the speed or velocity that the particle is moving, again multiplied by that strength of the magnetic field it's moving through. But since they're forces, all of that would cancel out and we would see a number that's measured in newtons because it's the force that is pushing on either that wire or that particle.